Okay, we're going to get started now. This is a time for our panel review and discussion. And again, the format's going to be pretty much the same. We've got Hugh over there ready to defend himself in the far corner. He's got his boxing gloves on. We're going to start with a presentation by Katie Walton-Day with the U.S. Geological Survey. She's prepared some PowerPoint presentation with a number of points. And Hugh, you know, if you want to answer at various points along the way, feel free to do so. And then when they're finished discussing, we'll have the rest of the panel come up and have some further discussion on the water quality issue. And I might just say, again, water quality obviously is a very important thing. This tells us the current conditions at the site, and I think we're seeing some indications of the effects of lithology and perhaps mineralization on some of the water quality in places. This is an important thing. It's an important thing in terms of if the site is mined, it should not be perturbed too much beyond the condition that we're seeing now. And on a closure, this is sort of the goal that we want to aim for, is to return it as close as possible to the water quality conditions that exist right now. So, without further ado, I'd like to ask Katie to come up.
Thanks, Kirk. So this slide illustrates how I've divided my comments here. I took the charge that we were given fairly literally, in that we were supposed to try and describe whether or not the data are credible, whether or not they're sufficient, and to try and help the audience understand what these data mean. And with water quality data, one of the ways that the primary way that you understand if it is the initial data are good is you do quality assurance, quality control methods and techniques. And what those are a series of techniques and samples that the project implements to understand if the samples that they've collected represent the real environment. And I'll go into that in a little bit more. And in the little discussion that I have here, I'll talk a bit more about how duplicate samples and blank samples are used to help assess the quality of the environmental samples. I'll also talk a little bit about some of the sampling methods. Are they sufficient? Are they credible? And then go into more of the water quality data. And after each of these topics, and certainly during the topics, if there's something that you can address immediately that he wants to, that would be great. My charge with the document was mainly to look at the water quality chapters. And there are some other water quality data in other chapters that I may have missed. There are things in the chapters I reviewed I may have missed. So if I miss things, I'm certainly welcome to hear that. But I think there are a few things that could be done differently. So what I'll do in each of these topics is I'll talk first of all about things that I saw that helped me get confidence in the data, and then go into things that I saw that may have decreased my confidence in the data. So hopefully I can describe these to people all here in terms that you understand, to get us all on the same page. So a quality assurance, quality control program is mainly put in place to assure good accuracy and precision. And if you think of a target, with the center of the target being the true water quality of the sample, or the water quality as it is in the environment, we pull that sample out of the environment, put it in a bottle, send it to a lab, do all sorts of things to it, and we want to make sure that the final number we get out of that bottle represents what we took out of the environment. And so the upper left diagram shows the ideal thing that we are aiming for. We want to have all of our samples, sample values, if you will, have good precision and good accuracy. So those 5 or 6 dots in the middle of the diagram might indicate different samples that we have, but we want all of them to come in close to the value, to the bullseye. If you move to the upper right, our analytical results are all fairly close to each other. That's called good precision, but they're not close to what was in the environment. So that's called, that group of samples has poor accuracy. If you go to the bottom left, if you took an average of all those samples, they'd end up near the bullseye. They'd be good. So they have good accuracy but poor precision because the values are also far from each other. And then in the bottom right, you have both poor accuracy and poor precision. So you have samples that not only aren't coming close to the average value isn't close to what it could be, and then the average value is far from the environmental value. So what we're aiming for in a sampling program is the upper left, to have both good accuracy and good precision. And so the things that I saw in the EBD that helped increase my confidence in the data that the QA/QC was done correctly is, number one, there was a collection of numerous and appropriate types of quality control samples. Secondly, there was detailed analysis of these results, and in most cases, good documentation of the results, but that was one of the places where I'll show you later that I had difficulty following some of that documentation or finding it in the document. They had a good QA/QC plan with several components that are listed here. Again, precision and accuracy, the first two are the ones I'm going to talk mostly about. They have written field sampling plans so that it was clear that they were trying to get everyone on the same page out in the field and in the office. They had quality assurance project plans associated with all the field sampling. There's some indications of good accuracy in that they submitted samples to look at accuracy. Now remember, that's telling if you have the right value. And the way that a QA/QC plan does that, there's several ways, but what this plan primarily did was they had, in the lab and in the field, they had what are called spiked samples. And so they added a known concentration of the analytes to the samples, and then when the sample went through the laboratory, they made sure that that concentration was what was measured, that they were able to recover that concentration. And those results were generally really good. One thing I couldn't tell with those was if the spike concentrations were similar to the environmental concentrations. So that was one thing I couldn't find documentation of. And that's important because if your spike is huge and your environmental concentration is small, then the accuracy you get from your spike really has no relevance to the samples you collected. You want everything to be in the same general range. But I think those data exist. They're just so detailed in 27,000 pages. Where are you going to put all that too? So I think some of these data exist. They just might not be in the EBD, but maybe there'd be a way to summarize them somehow in future documents. Another indication of good accuracy was they did proficiency evaluation samples. And what these are samples that we know the concentrations of the samples, and they've been certified by a laboratory. So a laboratory somewhere has done a mixture of samples of, different elements into a sample. Then that sample is submitted to the laboratory where you're doing analysis, just like it's a regular environmental sample. So it's called a double-blind sample. The laboratory that's getting the sample can't tell that it's a test for them. And so they just treat it like a normal environmental sample. And the results of those samples generally came out good. The second question for those performance evaluation samples is then similar to the laboratory spike samples. You want the concentrations in those samples to be similar to what you're measuring in the environment. And in some of the earlier PE or performance evaluation samples, the concentrations seemed rather high relative to what was in the environment, but then in later plans where the results were reported, they were much closer to what was in the environment. So that may have been an adjustment that the project made with time. But again, those are all good indications that we have good accuracy. Another thing that indicated attention to the details of the data were that there were some problems discovered early on in the total versus dissolved. Now what this is that when you collect a water sample, you will collect a sample that you don't filter for analysis, and you call it the total sample. So it's everything that's in the water sample. And then the dissolved sample, you run the water through a filter, so you're removing particles. So what you would hope to see in your total versus dissolved samples is that there's more in the total sample than there is in the dissolved, because you remove things with your filter. Well, what they were seeing early on was the opposite. They had a higher, they had some number of samples where dissolved was greater than total, and so they went through a process of trying to track down what caused that problem, and they experimented with several different solutions and looked at the results, and they seem to have solved the problem through time. So that shows that they're watching the data, they're analyzing it as it comes back from the lab. They're just not piling it up and waiting till the EBD is due to do it. They were doing it through time, modifying their techniques. So they're good attention to detail in that way. And keep in mind, this you think there are a lot of pages of data in this document, but there are a lot of results, a lot of water quality results. This is a huge water quality sampling program. So the QA/QC is an enormous task. I also saw some things that somewhat decrease my confidence in the data and prevent me from understanding whether or not the data are in that upper left, where we want the data to be, the upper left target. The Appendix A, which is a QA/QC appendix, has a lot of confusing terminology and it's difficult to read. I really tried hard to get my head into that appendix and really understand everything that they did, and some of it still confounds me. One instance is we could not locate the raw cation anion balance data. It was not in the Chapter 9 tables, as the text in Chapter 9 seemed to refer to it in those tables. We couldn't find it. So I requested and was given access to the DQARs. I read one of them in detail, and another one I skimmed, and I couldn't find the cation anion balance data. So we were able to decode and get a hold of all the water quality data eventually, but we weren't able to complete or even begin that analysis till late last week. So I'll show you one graph from our own analysis of the cation anion balance and explain why we think it's pretty good. And it verifies in their documents, they said the cation anion balance was good, that 99% of their samples passed their criterion, but we couldn't go back and find the data that supported that. And the cation anion balance, let me explain that a little bit. The cations are the positively charged major elements that Hugh talked about in his presentation: calcium, magnesium, sodium, potassium. And the anions are the negatively charged things that are there in large concentrations: sulfate, chloride, bicarbonate, carbonate, primarily in these waters. And water sample doesn't have an electric charge, right? You don't get shocked. It's neutral. And so the cation anion balance is a logic test. Because water samples don't have any electric charge, the sum of all the positively charged things in water should be equal to the sum of all the negatively charged things in water. And it's a logic check that you can use to see if your analyses are good or not. So that's what the cation anion balance is. There was a bit of a lack of variety of graphical presentations of data, and I'll show some examples of what I mean. When I'm used to dealing at the USGS, when we have long-term data in my office, we do a lot of different graphical presentations of data to see if the data fit in with the historic data, and we use that to look for outliers and as a way of telling whether or not we need to send samples back to the lab, or in the worst case, we need to delete them from the data set. And then I'll go into a little bit of detail on precision and accuracy. The duplicate data, the way it was presented, showed a lot of high variability. I actually think that's probably okay because of the low concentrations in these samples, but I couldn't evaluate that independently because I couldn't find the concentrations in the duplicate samples. I could just find a percentage number that indicated how far apart they were from each other. And in the blank samples, I saw some evidence of some contamination. There would be ways to deal with that contamination, to try and track down what was causing the source of contamination. I didn't see that that was done, and maybe it was, and if it was, please correct me. And but then also, once the blanks received a certain kind of coding in the database to indicate that they were contaminated, some of that seemed a bit non-standard to me. It may be referenced to EPA documents, but I think in the EBD it would be good to say if these things were professional judgments specifically in these instances, or if there's some reference that describes the techniques that were used. These would be very helpful to someone reviewing the data. So this is a representation of this cation anion balance, and it shows two different things. And these are the data that we were able to unlock and decode, and these are for Upper Tularet Creek. And the x-axis here is the charge imbalance, or the cation anion balance. And you see the cloud of data in the center of the diagram shows that those vary from about minus 20 to plus 20%. Now, the way that we did the charge balance actually is you'd get a number that's 2 times the way that Pebble did the charge balance. So this would really be minus 10 to plus 10%, and I did not have time to go in and change all the numbers and do that. So already a pretty tight charge balance representation. You can see there are a number of samples that lie outside those charge balance. There's a bunch down on the y-axis at this line at 100%, and those are samples that didn't have conductivity measurements. The other thing that's shown on this diagram is a non-standard, and it's a new thing. It's in a paper this year in the article Geochimica et Cosmochimica Acta by Blaine McCluskey. And this is a technique that I think is really useful as a screening technique to look at the quality of water samples, water quality samples. The y-axis shows a specific conductance imbalance, if you will. And there's a way to do a similar thing with specific conductance that we do for charge imbalance. And you can calculate specific conductance related to your analytical values and then compare that to what you measured. So that's what this imbalance is. And what it can show you is if you have a bad charge balance, if your charge balance isn't within your tolerance, you can use this diagram to decide if either your cations analysis are bad or your anion analyses are bad. In this case, the cloud of data pretty much spans, again, on the y-axis, I apologize, these numbers are hard to see, but 20% to plus 20 to minus 20. So they're distributed evenly around the y-axis, which would indicate there's equal problems with both positive and minus analyses of positive and minus charged species in your sample. So that's fine. I mean, it kind of normalizes out. So our initial reevaluation of the cation anion balance is that it's probably pretty good. Now, if you read the QA/QC appendix in any detail, and I'm looking at people in the room who know it, 10% is much larger than the tolerance that the document specifies. But these analyses have very, very low amounts of solute in them, and so at that low end of the solute range, the document had a very kind of a wide tolerance in recognition of how hard it is to get analyses at those low values. And so I think in the end that these numbers are within their tolerance. I haven't verified that because you'd have to do a few more calculations, but it gave me confidence that what they've done with the cation anion balance is probably okay, even though I couldn't find it in the document. Some graphical tools that you can use to check data quality are element versus element plots, discharge versus element, so stream flow versus element. Seasonal plots, we saw some of those. Time series plots, we've seen some of those. Concentration versus discharge. We've seen some of those for average values at sites, but what I'm talking about are at individual sites. So you have a cloud, you have a bunch of data from one site, you get your 2009 results in, you plot them versus the old values and see where they fall. So let's just look. These are, again, a screenshot of some of our stuff, but I think you can see in general what I'm trying to say. The upper left graph shows a 5-year time series, and the lines there are stream flow, and then the dots are the samples. And one thing that's a little hard to see on the left-hand side is a box and whisker plot like we were looking at that Hugh gave us. On the upper left graph, on the very left-hand side near the y-axis, there's a little skinny box and whisker plot. Yeah, sure, people online can't see it. Right over there. And what this shows you is the historical range of all your samples at that site. So you have an immediate visual cue if your samples aren't falling in that range that you've got some outliers. And so those would be things you might want to send back to the lab, look at the documentation, see what's going on. The next graph on the upper right says monthly grouping. So the months are represented as numbers on the x-axis and the concentrations on the y-axis. And you can see how the concentrations at this site vary through time. And your new samples have a different color. They're blue. And so what you're looking for is, do these fall within the range of what we've measured before? And they generally do. And you're making some assumptions here that nothing is changing at this site. So if you get outliers, it might indicate that you have a bad value, or it might indicate that something's changed at the site. Also concentration versus discharge in the lower left, and in the EBD they did talk about how some things varied with discharge in a general sense, but this would give you more detail, and you could see if one of your samples plotted up here, for instance, something's going on, and you might want to look into that. And then concentration versus specific conductance. Similarly, your new samples are plotting in that area, these big blue dots. And so it gives you some confidence that these numbers are representative of this site. This isn't all that you do, but these are just some things that you can do at sites where you have a lot of data like you guys do that might help you track down problems as you're going through QA/QC. Another thing would be element versus element plots, but so you'd have one element on the x-axis and one on the y. So at some sites where you have a lot of trace elements, you might want to plot copper versus zinc or something and see these relationships, and they might help validate, or excuse me, verify the numbers that are in your that go into the database. When I look at samples, duplicate sample values, I want to know the value of the duplicate concentration, but also how different the two samples were from each other. So duplicate samples are two of supposedly the same sample. So when you're in the field, if you're taking a field duplicate, you split your sample into two bottles and you submit them as separate samples. And if they go through all the same procedures, and so you should get a pretty tight number on those duplicates. And then and Pebble did that type of duplicate, and then they did another type of duplicate, triplicate, where they actually took 3 samples. And the first 2 samples they submitted to their regular lab, and then the third sample they submitted to a different lab to check the lab. And so you'd expect those 3 numbers to come up pretty close to each other. And there are different ways of representing how those numbers look. And this is one way that I think is very helpful, because it shows on the x-axis the concentration that's in your duplicate sample, the average concentration of the 2 duplicates. And then the y-axis represents how far apart the numbers were. So the closer you are to 0, the better the analysis. The farther you are from 0, the worse. But the thing that this represents really nicely is that analytical techniques have a lot of trouble at low limits getting really tight analyses. So it's really common to get different numbers, widely different numbers. If your analytical detection is 1 on your method and you submit a duplicate and one of them comes back as a value of 1 and the other one comes back as a value of 2, you might have 50% difference in those, but it's not that bad. On the other hand, if your analytical method is capable of seeing down to 1 and you submit a duplicate and one of them is 50 and the other one comes up as 100, you're way up in an area where the technique is probably pretty good at seeing that element, and you should expect much tighter. So to get 50% error way up high is bad. So what this graph shows is that the lower values, you can see more difference or more error in those duplicates. And then as you get higher values, you actually overall kind of see lower error, although this smoothed curve here, because there are fewer samples out here, shows that you have more error as you go. So 2 things here that help see what's going on is showing the concentration of the duplicates and then showing some kind of trend through the duplicates. So the way the duplicates were shown, at least where I found them in the Pebble document, and actually this was for the triplicates, and this might be where someone wants to correct me if I'm wrong, because it took me a while to figure out what this diagram means. I think I get it, but if I don't, please correct me. So on this diagram, there's a line at about 20% difference, and this says average, and this represents all the duplicates that went to their primary lab. So they had an average of 20% difference, which isn't bad. Then their upper confidence level is a representation of how the range of differences they saw. So their average was 20, but their percent differences in that primary lab ranged up to 100%. And so then all the red dots are the triplicate sample that was sent to the second lab. And so they're trying to compare and see both what the range was of those values and how they compared to the first lab. And in this case, I believe in the document there's a table that says the average of these red dots was about 32%, so somewhere in here. And then the range, if you did the range the same way, it would be plus almost 100, so up to somewhere in here. would get most of the samples. And so there's a difference between the two labs, and they seem to say in the document that this was acceptable. And I think ultimately it is because the concentrations are low, but I had no way of verifying that. I could not find the concentrations of the duplicates, and I certainly would be hard-pressed to replot them all in the way that I think would help understand them more, like this. So that made it tough for me to evaluate whether the duplicates were done well, and so therefore what the precision was of the data. I didn't talk. Blank samples are another thing that you do to see if there's contamination. And contamination's a problem because in waters that are as clean as these waters are, if you contaminate the samples while you're collecting them, you're collecting non-representative samples, and it skews your data set. So what do you do for a blank sample? You put clean water through your equipment or your procedures, basically. Why are you doing this? You're trying to assess when, where, and how contamination is occurring, and if contamination is occurring. Why do we care? Contamination causes, as I mentioned, inaccuracy in the samples, so we're not on the bullseye. Most importantly, at a site like this, you lose a lot of detail at lower concentrations. If you have contamination, you have to eliminate a lot of data from your data set or code it in a kind of a funny way that you might not include it in all your calculations. It alters the distribution of the data. It changes those box and whisker plots that Hugh was showing. It changes their shape, particularly at the low concentrations. Some of the blank samples that were run in the program were method blanks. These were to test contamination at the lab. Deionized, DI stands for deionized water, so this is water that's supposed to have nothing in it. It tests for contamination in the blank water that you're using to rinse things. So the water you're using to test for contamination should be contaminant free. There were some hits, and there were some what I call hits or contamination in those. And then equipment rinsate blanks. They take a blank and they pretend it's a sample, take clean water, pretend it's a sample, run it through all their procedures, and collect that water just like it's a sample and submit it to the lab. It should come out clean if their cleaning procedures and their equipment are clean. So there were, as I said, noted on this slide where the 3 asterisks are, there were some hits in the DQAR that I looked at, which is a Data Quality Assessment Report for August 2006, in both the DI water blanks and the equipment rinsate blanks. The contaminated DI water might be a result of just using, the laboratory sends the water to the project, is my understanding, and if they're just sending their laboratory process water, then a certified blank water, that could be the cause of the contamination in the DI water. They also had contaminated rinsate, and so I went into their field sampling plans to see what their cleaning procedures were. And between sites, they were washing equipment with soap and deionized water wash. And at the low concentrations that they're expecting at this site, it would really be best to add an acid wash step. Now, I certainly appreciate when you're flying around to sites in helicopters and whatnot that carrying acid around is not an easy thing to do, but the way we deal with that is that we have dedicated acid washed equipment that goes out to sites. So if you're sampling 10 sites in a day, you have 10 sets of equipment ready to go. So it entails having a person back at your base that's doing some acid washing in between trips to keep all this equipment clean and get it ready to go. And when the equipment is clean, it's double bagged in plastic bags, creates a lot of waste, but that's what you have to do to keep it clean. You're getting in a helicopter, there's a lot of metal around, there's a lot of dust around. You have to keep the equipment isolated from the environment to keep it clean. So what I didn't see was that what happened with the blank data then was that they were coded in the database, but I didn't see any evidence that they went back and examined why the blanks were contaminated and try and address those problems. As I mentioned before, they did do this for the total versus dissolved, but it didn't seem to be done for these hits. And if it was done, I'm wrong and I apologize, but I couldn't find it in the document. So the environmental data that were associated with these blank data. So you collect these blank data, but then you're collecting a certain amount of environmental samples that day. All those samples that had concentrations that were less than 10 times their method reporting limit were considered contaminated as well. And this is prudent and the right thing to do. Data above this concentration are not contaminated. But then the question is, how are these data included in graphs and calculations? If you have all these data coded as being contaminated, you've changed the low range of your data set by calling them contaminated, and it's not clear to me how they were then included in the calculations. So the effect in a contamination is you get loss of detail at low concentrations, which in this site's really important because you have low concentrations, and it biases or skews your box and whisker plots then to greater than the real concentration. So we move off that bullseye in terms of accuracy. So that was my longest of the 3 sections, and I'm happy to pause here, and I would really welcome having some of these comments addressed now, if you guys are prepared to. Jane, maybe? Yeah.
I started on the project in 2004 as the analytical QA/QC manager, so I set up this whole program and was involved in the preparation of this part of the EBD and all of that. So, I mean, I wrote down my notes here. There might be some things, but I can start with the first thing I noted was your question about the concentration of the matrix spike and matrix spike duplicate spikes. And you're correct, the laboratories, they have a standard protocol that they use a concentration that's the same for every sample that comes through the lab. And we did not specify to the laboratories a different concentration than their standard concentration. So there may in fact be some analyses where those concentrations are well above our project water quality concentrations. So we did not direct them to do anything different, just so you understand that.
Okay.
Excuse me. With regard to the performance evaluation samples, in that case, we did look at our site-specific concentrations and direct the company making the performance evaluation sample. We gave them the ranges and we asked them to prepare those samples to mimic the field concentrations so that the lab was less, they wouldn't have a clue from that, that these were performance samples.
Mm-hmm.
So that's what we did for performance evaluation samples. And then your question about the cation anion balance results. What we did there is we required the laboratories to do that calculation during the course of analysis so that they looked at that criteria and they could go back and do a reanalysis more real time and adjust the cation anion balance so that it met criteria through doing reanalysis, and that's reported in the laboratory reports themselves. Okay. So that's why you're not finding that.
Okay.
It doesn't appear anywhere else right now.
Sure.
Okay, what else do I have here? I wasn't clear on your comment about the non-standard approach to the QA/QC assessment of blanks. We use national functional guidelines for that.
Yeah, and I think the only thing I meant there was the 10 times. I don't think you need to be that stringent. Sorry, gotta find it.
Okay. Well, that might be more conservative.
Because I think there's a 5, because I was looking through some of those, the rags, the EPA rags, and the 10 times one I think was for like weird ethyl butylene and some really strange things.
It's real common for volatiles.
Yes.
Because some laboratories have these volatiles in the laboratory air, and so they really make a high multiplier for that because the concentrations can be such that 10 times is common in the lab. So that's where that comes from.
But I guess I wondered if you might consider lowering it to 5 times.
Yeah.
Because then you'd lose less data.
Right.
And you have documentation for that. It's in those standard approaches.
Right.
I mean, I appreciate being more conservative, but you're losing data.
Well, what we did was we flagged the data B to alert the user that it has this contamination, but that data didn't get removed from the data set that went to Hugh and to Mark Stelgius for the evaluation.
Okay.
And so it was not excluded in all of their plots that you see in the EBD. That data is all included.
It's all there.
Yeah.
Okay, with the original value.
Yes.
Okay, that's good. That's good.
Okay.
Thank you.
What else? Well, and your input about the acid wash, that was helpful. I wish I'd have known that 8 years ago. Well, I wish I'd have done that 8 years ago. So that's a good advice there.
There are details in the USGS field manual about that.
Okay.
And I'd be happy to talk to you about it too, just how in practicality, how you implement it.
Yeah. And then the other thing, all of our assessment of blank results are in the DQARs. You're not going to, it's
Okay.
not, there's not much of that in the EBD analytical QA/QC.
Okay.
And as I've actually looked at it recently and realized that there's some, it would be hard to assess some aspects of the work from that appendix by
Well,
itself.
Yeah, I mean, it might be helpful, for instance, in the duplicates, there's a lot of cross-referencing in chapters like C, the QAP, or C,
Yeah.
and so, for instance, when you're presenting the duplicate results, if you also just in a column presented the data quality objective for the duplicates in that column, so that the reader doesn't have to go, to another appendix and sort through that and find it. I mean, the data quality objectives were pretty similar for most elements. I mean, it was 20% and 30%, I think.
Right, that's right.
Yeah, and so that it would be pretty easy to reference those where the data are being presented rather than referring the user to somewhere else.
Okay.
And I realize since different people wrote different chapters, I think there was a lot of attempt to minimize that kind of thing. But in the QA/QC, it was really you were going to a lot of different chapters to find things, and it was hard to find them. So
Okay.
I apologize that I didn't find things. So
Okay. I don't know if that covered
yeah,
all
I
of your
think
points.
I think that was very helpful.
Okay.
Yeah, so the data, like on this slide, the data were then included as their raw values in the graphs and calculations. So that's good to know. Thank you. Hugh, did you want to say anything about that? Or?
No, I talked to Jane enough to be satisfied that things were dealt with in the QC program in a pretty rigorous fashion.
Okay.
She's the one that has the most insight.
No, I mean there's a lot there, and I, appreciate you responding.
I think your suggestions are really quite helpful.
Okay, I mean I hope so. I'm not trying to make it harder to do an already difficult job. Sampling methods increase confidence in the data. I was impressed with the coverage of stream flow and water quality conditions through the years. What I mean is through the year, through the season. Getting out there in the winter. I mean, Jamie indicated sometimes they had to bivouac overnight in the winter. That's not an easy thing to do. It would be really easy to say that we're just going to do it the ice-free periods, and they didn't. And I think that shows due diligence. Also, the collection of stream flow and discharge with almost every water quality sample. I realize that was done for the hydrology program, but I hope to maybe show you how it could be helpful in understanding the water quality as well, in addition to the ways you've already integrated it. You collected an integrated sample at least, I think, after the first year across the width and depth of the stream. This is really important because, and what I mean is they didn't just take their sampling device, go to the middle of the stream and dunk it and get the water. They tried to collect water all the way across the width and the depth of the stream, and there are certain techniques. This guy is showing you one of these techniques right here. This sampler, he can raise and lower this, and it's got a nozzle on it that allows water in. So if he walks across the stream and raises and lowers that bottle at the same rate every place he's going in the stream, the amount of flow in the stream determines how much flow goes into his bottle, and so he gets a flow-weighted sample of the stream, which is really important if you have groundwater coming into the stream or if you have tributaries coming into the stream that haven't mixed. So, for instance, if you have some sort of seep on this bank of the stream, if you just collect in the middle of the stream, you're going to miss that. But if you do this integrated sample, you have much better chance of getting that. I was also, it helped increase my confidence in the data that they added and subtracted sampling points each year. It shows that they were reviewing the data, they were looking at it, they were trying to understand what was going on, remove redundancies and fill in data gaps as they went, not waiting till some sort of written report was due. I also thought the low flow sampling and analysis was necessary and was done in a good fashion. Some things that decreased my confidence in the data, there were some items in the sampling plans that weren't mentioned in the results. In particular, there was talk about hypereich zone sampling. Hypereich zone is a zone of the stream channel where groundwater and surface water are mixing. And when you have groundwater, surface water interactions like you have in this stream, it's important to try and understand what's going on in that zone. So the initial sampling plans talked about installing some equipment to try and understand that zone, and I didn't see follow through. Maybe it's coming out later. Maybe it got nixed because they felt that the surface water measurements were taking care of that for them. But I still think that that's maybe a potential data gap, that stuff should happen because it could be important to understanding the biology of the stream as well. I just said that I liked that you collect integrated width and depth samples. So what's this statement doing on this slide again? I think you could do it in an easier way. It looked like from the sampling plans that what you're doing is what we call at the USGS a discharge, equal discharge sample. And so to collect that sample, what you first have to do is measure the stream discharge. Then you have to divide the stream into equal discharge increments, and they chose 8. So the stream gauger gets a measurement. Then he has to calculate everything out right there in the stream. Then they put a tape across the stream, and the stream gauger says, okay, if I divide the flow by 8, then your first 1/8 of flow occurs in the first 3 feet. Your second 1/8 of flow occurs in the next 1 foot, because that might be a really fast-flowing segment. And so then you're supposed to go to the middle of each of those segments and collect the depth integrated sample. And it's tedious and time-consuming, and it means that you have to wait until your stream discharge measurement is done to take your water quality sample. And so I don't know if that's exactly how it was sampling, if it was done that way or not. An easier way to do it that gets the same result is what we call the equal width increment sample, and these are all in the field manual that's online. But the stream sampler can spread a tape across the stream and take those depth integrated samples at equal width measurements across the stream, and it has the same effect, and it's a lot faster and easier, and it allows for the stream gauger and the water quality people to be working at the same time rather than have to wait for the water quality people have to wait till the stream gauger's done. So it's an easier way to do it, and but I couldn't verify really how it was done. The way it was described sounded like the harder way, but I couldn't find any documentation that it was done exactly that way. And a lot of times we have notes like that on all our sites that would not end up in a report. They're in the archive. They're in the files. So maybe that information is in archive files. I saw some mention in the plan about stable isotope analysis, but I didn't see those results. It was only for the seeps or the ponds, maybe, to look at evaporation. I'm not sure. But I think that stable isotopes could really help understand some of the surface and groundwater interactions, particularly where you have the upwelling water in the South Fork Cook Tule. Is that the same water that was lost further upstream? The isotope signatures would help you understand that. Is the water that's coming out, the supposedly transbasin flow in the upper Tulare, is that really the same water that's being lost? I think you have good groundwater evidence, good pressure evidence, but it'd be nice to support that with some geochemical evidence, not only isotopes but other things. The specific conductivity calibration was done according to manufacturer's specifications as far as I could tell. The problem is that the manufacturer has you calibrate your instrument at 1,000 microsiemens per centimeter, and most of your samples are less than 30. And so what we do when we have those situations is we do checks. When we calibrate the meter with the higher standard, we then do checks with a bunch of lower standards. So I'm starting to speak Greek, I'm sorry. So specific conductance is just that one of those index parameters that Hugh referred to. And when you measure it in the field, you have a meter, and you have to calibrate that meter so that the meter is measuring the right concentration for you. What the meter reports is near that bullseye. Basically, that's why you do a calibration. But if your calibration concentration is way different than what you're expecting in your samples, you don't know if your calibration if your meter is doing a good job measuring your samples. So all you do is you measure a couple of other commercially available standards whose concentrations are closer to that you would expect in your samples, and you just have notes, you include in your field notes that the buffer that's 100 microsiemens per centimeter read 102 microsiemens per centimeter. And then that gives me confidence that your low conductivity measurements with that meter are good. It's not something that the manufacturer necessarily recommends, but and conductivity is a pretty stable measurement, but it's still something that should be done to increase confidence in those low values. Finally, I listened to some of the and watched some of the presentations from January, and I noticed that Bob Seal at the USGS got up and asked, were diel patterns considered? And I'll go through what those are in a minute. But first of all, I'll say that diel patterns in streams were not well recognized publicized when you did this initial sampling. So I'm not trying to criticize you for not doing them, but I'm suggesting that you might want to look at them as this goes forward. What are diel metal cycles? Maybe ignore the graphs on the right for a minute, just to understand this strange word. Diel just means 24 hours. These are cycles that happen in streams over 24 hours. What they can do, though, is the metal concentrations are actually varying with time, and it's not because the flow is varying or anything else. It's because in-stream processes are varying. And we can see concentration ranges as great as an 800% change in the concentration of zinc over the course of a day. So this middle diagram, zinc are the open circles, and you can see the minimum zinc concentration is about 10 micrograms per liter, and it goes up to about 80 micrograms per liter just over the course of a day. So if you collect a water quality sample here that you're going to compare to ADEX standards, you have a greater chance of exceeding the standards there than if you collect your water quality sample here. So it's really important if you're comparing numbers to standards and if you're trying to understand downstream trends, all sorts of things. Where does this occur? It's been documented mostly where the pH is neutral or greater than 7 in the western U.S. at many, many locations. It's not an isolated thing. Why does it occur? The current thought is that in-stream processes, there's a lot of algae and things in the stream, and that photosynthesis and sunlight cause the temperature and the pH variations, temperature and pH to change during the day. So this lower graph shows temperature in the dark dots, and you can see that temperature, I should mention these shaded areas are nighttime, and the bright areas are daytime. Sorry, I didn't say that sooner. So temperature decreases through the night, increases through the day, and pH does the same thing. And when this happens, the stream bed and particles on the stream bed can actually hold on to some of the metals depending on the pH. They'll grab the metals, and the metal, it's called sorption, when the metals move from the water column down to the stream bed. And sorption is very dependent on what the pH is. So as the pH changes, the sorption changes. And this is documented in a paper by Dave Nimick and others last year in the journal Chemical Geology. So you're probably all going, come on, Katie, it's Alaska. The sun never sets, right? It doesn't. We don't have nighttime in the summer. But I looked at the USGS gauge, one of the gauges in the Pebble study area for the. I just really quickly looked at the temperature record for late June and early July this year. And the temperature up there does vary on a daily basis by, at the height of summer, a couple degrees centigrade. So I would guess that these patterns would be less pronounced for you. But I think they might still exist, and I think it's worth trying to collect some of these samples. Well, come on, Katie, if we put an auto sampler out there, a bear is going to take it down. Or, I mean, it's really, and we don't want to be, do people have to camp out at the stream all night? What are we going to do? There are ways to do it. I mean, you could have people camp out all night. I think David's data, he doesn't believe in automatic samplers. He's out there all night long doing this. But I do it with auto samplers. But what I'm saying is I think it's worth it at one or two critical points to look at it, to try and figure out a way to get a handle on it, and if it's important, because if you're comparing your numbers to water quality standards, this could be key. And unfortunately, David's done a really good job in spreading the word about this, so people know about it. It's becoming a bit of a game changer in the monitoring world. And so if you guys, nobody, as far as I know, is John, is the USGS, where's my USGS guy? I don't know that anyone in Alaska has done this yet. Is anyone in our office here doing this, trying to look at it? Okay. And I don't know if anybody's trying to do it. So, it'd be groundbreaking research, too. So. Well, it's light then anyway. I mean, I'm just suggesting it might be something you want to look at. So. Oh, that's a great question. Is this true for all metals or just some metals was the question. And it turns out it doesn't seem to be really important for copper, but this diagram shows some things that might be important to you. Zinc is a real persistent contaminant in streams, and so it's important for zinc, manganese. You can see arsenic there. You don't have much arsenic. So maybe, maybe if copper's your primary contaminant of concern, you don't want to worry about it. But zinc could be a problem later on here. So that, it might be something you want to look at in the baseline just to see. So I didn't know, I was pausing one more time before the finale to just see if there's comments.
Yeah. So I'll speak to these things. It seems like the diel metal cycles is worth considering. I'm not sure that we would want to go ahead with it, but I think you're right. It's something that should be evaluated and looked at, and we can either sign off on it or not, and have a rationale for why we would or would not evaluate those metal cycles. The hyporeic zone, that's a topic that's been on the table for almost ever since I joined the project, and it's gone back and forth as something that is regarded as potentially relevant or not relevant, and currently it's under discussion again. And there's been no commitment made at this point, but the direction that it's going is to do some evaluation of the hyporeic zone. So that's the status with the hyporeic zone. The stable isotope evaluation is also something that's been on the table for pretty much ever since I've been on the project, and what I haven't wanted to do is I haven't wanted to do a stable isotope evaluation sort of 25% or 30 or 40%. It is kind of, if we're going to do it, then we should really go all the way and be thorough in the evaluation. So, and my own view is like in my groundwater investigations, I've had some very good results looking at different types of isotopes related to geochemical processes and that sort of thing. So in general, I view isotopes as a potentially very powerful tool. And if it's going to be one of your recommendations in your report, then I definitely see it as something that's worth evaluating.
Well, and I would suggest maybe you don't need to go full bore at first, that maybe you'd want to sample, see what kind of variation you have, where you'd expect to see it, if you have enough variation for it to even make a difference.
Mm-hmm.
I mean, you have precipitation coming in from different elevations, so you should see some variation, but there's not a huge elevation gradient at the site, so maybe it's not useful, but it might be good to either randomly select sites or purposefully select sites where you expect to see variation and see if it's there. And then, just because they're so easy to collect, they're just raw sample in a little vial.
Yeah.
It's not hard to add it to a sample schedule and just do it. So,
Yeah, fair enough.
okay. Anything else? Or do you want me to go back or anything? What was it? Diel, hyporeic, integrated depth width.
Yeah, the integrated samples. Yeah, I wasn't involved in the design of the sampling program for the surface water, so I'm afraid I'm not the best person to speak to that question.
It's just, it'd be nice. I was trying to make, first figure out what you did, but then maybe suggest something that might work better. So.
Yeah, fair enough.
Move on. So then water quality data, what Hugh presented. What did I see there that increased my confidence in those data? One thing that hasn't been mentioned is that they measured dissolved organic carbon, which seems kind of obscure, but the water quality criterion at the EPA are evolving towards, for some metals, particularly copper, using an equation called the biotic ligand model, and rather than table value standards or hardness-based standards, and I'm speaking Greek again, but there are different ways of coming up with water quality standards in the regulatory community. And this biotic ligand model is a new way that's gaining some traction, and you have to have a dissolved organic carbon concentration to calculate what your standard is at your site. So it's good that you have that, because that might come in handy later on. The general results are that you have this very, as we saw from Hugh, very clean water with low alkalinity, generally low metal concentrations, low hardness, and this is consistent with expectations, what we'd want to see based on the geology of the area. So that increases my confidence in the data, just that what we saw is what it makes sense in terms of what's there. I'd be surprised if it was different. Also, one of the things you mentioned is there's some higher concentrations over the deposit. Makes sense. It's good. But then there were some other things, and this is that decreased my confidence in the data. A lot of this has to do with treatment of some of the data after it had come through the QA/QC process. And I'm referring mainly to the surface water data. Outliers are things that are either at the far high end of your concentrations and at the far low end of your concentrations. And there was exclusion of high and low outliers from the data set after the data had been okayed, had been through the QA/QC procedure. For example, in the small print there I say, and this is a little bit technical, but I'll try and describe it. Non-detects, so these are values that are below the detection limit of the method, were excluded from the analysis if they were, quote, higher than other data values or higher than other non-detected values, and therefore would have skewed the data analysis. So it sounds like from this that non-detects were excluded just because they were different detection levels or because there were other levels lower. And as Hugh mentioned in his talk, there's a variation of detection levels in this project based on changing labs, changing conditions, all sorts of things can cause the laboratory to say with one batch of samples, well, the lowest value we could see this time was 1. And then the next time your samples come back, they say, well, you know, we had some trouble at the lab, so the lowest value we can confidently say we saw was 2 this time. And so we're changing our detection level. And this makes it hard to analyze the data when you have different detection levels. But there are some techniques out there that, again, were not really widely touted when this report was written, but that are out there now. And I would encourage you to look at Dennis Housel's work. And he's an independent consultant now. He used to work with the GS, but he has methods for dealing with multiple detection limits that prevent you from losing that detail at the low end of your data set. Because what this exclusion of these outliers is doing is you're losing detail that you spent so much time and money to collect those samples, and then you're saying, well, we decided they weren't, that, you know, we're going to exclude these values for these reasons. There are a lot of them, I think, that you can keep in there that would improve keeping the data on the bullseye. When you exclude these things, you move the data off the bullseye, like I was showing in those earlier slides. So what I say is this probably caused a loss of accuracy. It probably moved you off the bullseye a little bit because you're excluding values that are legitimate. You just don't know quite what they are. But if you exclude them, you're saying, well, we didn't even measure that value. So their methods are valuable for dealing with this. The QA/QC procedure should be what you use to exclude values. If you're going to exclude high and low outliers from the data set after you've been through QA/QC, I think you need to document that rigorously as a professional judgment. Do you have an EPA document that supports doing that? Or as in the groundwater, it seemed like there were more valid reasons for excluding some of the data. What they noticed in the groundwater was that some of the initial they saw a trend to decreasing concentrations through time in the groundwater and for some elements, and then the concentrations would level off. And their hypothesis was that these wells were still not in equilibrium with the aquifer water. They were still responding to the drilling event. And so that they excluded some of those values, and they did a very good job of explaining why they did that. I think there's still some people out there who object to that, but I think it's good that it was explained and that it's something that made some sense. So I just think there could be better documentation of those outliers because it didn't make sense to me why they were excluded. And some of the data we looked at, Hugh showed us how he plotted median values. Remember those box and whisker plots that he showed that plotted the values moving downstream through time, and he said that there were downstream trends in metal concentrations. This is where I think you could use your surface water flow measurements better. We do what's called a load analysis, and I'm pretty sure all the technical people in the room know what this is, but for the less technically inclined, it's simply taking that stream concentration and multiplying it by the stream flow. And when you do that, you get, I'm smiling because there's some yawns in the audience. I need to wrap this up.
I'm excited.
Oh, good. Good. You multiply the concentration times the stream flow, and when you do that, you get a value of concentration divided by time. It's called mass flow, so it's milligrams per second or milligrams per day or pounds per day, however you want to do it. But if you're looking for sources of metal or constituents along your stream, you have to look at load. Concentration gets diluted as water comes in. It's not conservative. It's hard to look at concentration patterns and figure out what's going on. But if you're looking for either gains of constituent along your stream or real losses of mass, you have to look at load. So I would encourage you to use all that stream flow data to do some loading analysis. And by now maybe it's been done. I don't know if it's been done or not, but I mean, again, I could talk to you about that because it's a more robust way of trying to suss out what those graphs were trying to do. At least I think it is. So I probably should have removed this interpretations were non-standard. There was something in the document about the springtime decreases in alkalinity and hardness being caused by erosion of sediment, but Hughes said today they were just caused by I mean, you didn't directly say dilution, but you said it just showed that groundwater was a source of alkalinity and hardness. And so then when the stream is mostly rainwater, it dilutes all that alkalinity and hardness away because you're diluting it with rainwater that has very low, if non-existent, alkalinity and hardness. This next bullet, the fourth one, insufficient use of water quality data to support groundwater surface water interactions. I mentioned some of this earlier in the isotopes. It would be really nice to see in those upwelling zones in the South Fork, the Coktuli, in the Trans-Basin area, in the Upper Telluric, is the chemistry similar to the water that you lost right below Flathead Lake? Or has the chemistry changed? I think it would be nice to support those groundwater interpretations with more of the geochemical data. You have the data, you can do it. It'd be nice to see. And there was something about the molybdenum that was in. Wasn't it coming in that UT 119A? There was molybdenum in that, and so that seemed really distinctive from what was over in the South Fork. And I may be mistaking which tributary, but that might be the first thing to look at because there was something about molybdenum that kind of struck me that maybe that was being transported across the basin or something.
Now, certainly the molybdenum had an increasing trend.
Yeah. In the Upper Telluric.
In the Upper Telluric,
yeah. And so was that coming in the Trans-Basin flow, or was it just, I mean, it didn't look like it because it was consistent.
It didn't look like there was a jump. You know, it's like it was kind of like this. It wasn't like that.
Okay. And then the last thing I have here is that the groundwater quality data in the deposit area seems kind of sparse. There was only that one deep drill hole, and if you're going to be dewatering, you need to understand that water quality better. And I don't know that. I think there are probably more data by now, but I don't know. So then to wrap it up, I talked ad nauseum about QA/QC, sampling methods, water quality data. So what's my overall, take-home message is I think the plan is strong and robust, but detail showing adherence to the plan is confusing. There were a few non-standard, non-documented procedures. Maybe they were professional judgment. If they are, say it. Some confusing descriptions that decrease my confidence in the data. Now, I will say that based on some of the discussions we've had today, I think some of that lack of confidence has been alleviated, but there's still some lingering issues, I think. So,
I wonder if we could just quickly go back to
You bet.
a couple of your slides there, just in the last section.
this one or
Yeah, both of them.
okay,
Yeah, so I'll be the first to admit that we don't have the full answer on treatment of outliers because it's a potentially tricky business. But I will say that when I looked at the control plots that we had for the surface water data, and we had, for example, some detection limits here, and then some detection limits here later on, and then we would have detected values interspersed down here like this. I felt uncomfortable retaining those detection limits that were up there. Even though those samples passed the QA/QC criteria, just seems like with that particular parameter for those particular sampling events, it seemed like the non-detect there didn't seem to represent what might have been going on based on other sampling results at that location. So that was the rationale, and you know, I'm certainly open to considering other ways of looking at it, but that was the rationale for that.
I guess I think that once the data's gotten through the QA/QC, it's part of the data, and if it's an outlier, I mean, this is different. You're talking about a low-level outlier, but the high outliers might be telling you something about what's going on, and so if you're going to remove it from the data set, it might be better to go back to the QA/QC step and see if there's a reason there to remove it, not just the fact that it doesn't seem to fit the trends of what you previously know about the site. Now that kind of goes against some of those diagrams I was showing, but what I tried to point out, like when I showed some of the plots that we do for QA/QC of elements versus discharge and things, if we see an outlier there, we don't necessarily exclude it. We send it back to the lab. If the value comes back the same way, then we say, okay, this is real, something's changed, we need to explain it. So I guess I just am really, I would remove outliers from the data set as almost a last resort. It just doesn't seem like it should be standard practice.
And just as a note, for the surface water data, we did not remove any high concentration outliers.
It was mostly the groundwater. Okay.
Yeah.
I was just going to add one thing to that, which is there's almost always another chemical parameter that's varying in a strange way when you have a high outlier, and you should be able to pick up on that. If there's nothing else in the data that behaves like that one high outlier, that's a strong indication, I would say, of an analytical problem or contamination of that sample or something like that. And then, you know, you might have a better justification for throwing it out. But I'll always look for other chemical signals, other things that have changed in a similar way. And then again, as Katie said, that's telling you something about what's going on. We're running out of time.
Really?
And I'm going to do something a little unusual here. It's not quite time for open discussion from the audience, and I'm not the audience anyway. So, but we had an email that came in for Katie.
Oh, dear.
Okay, so this came from Ann Mace at Stratus Consulting. What did you think of PLP's outlier evaluation in Chapter 9? Should the ones removed have been removed? Should more have been removed? There's several questions here. I can repeat them. What did you think of their criteria used to remove values? And also, what did you think of concentrations of cyanide in surface water? Do you think they're real? For many of these, WAD cyanide was higher than total.
Boy, I'm not a cyanide expert. My understanding about cyanide is that it can be there naturally from bacterial processes, but maybe the WAD shouldn't be there at all if it's natural. So I can't address the cyanide. Did that question come in before or after I talked about outliers?
I'm not sure.
Yeah, is there a time on the email? Or no, it's just they printed out the time.
No.
I tried to address most of that. Sorry. It was before.
Okay.
So, Ann, if you're out there, maybe send Todd an email to let him know if I think I addressed most of that, but maybe I mean, basically, I don't remove outliers from most of my data. If it gets through the QA/QC, it's something I need to try and explain. I think if they're going to remove them, they need to have a little more explicit justification in the text as to why. If it's professional judgment, that's acceptable. Just say it. I mean, and there was some explanation, but it didn't make sense to me.
Yeah.
And it wasn't referencing standard techniques or professional judgment.
I think this discussion was a good one, but I think we've covered that very well at this point.
Okay.
Yeah,
Good.
thanks.
Just one small detail I'll add on the outliers that were removed is a very, very small proportion of the data set.
And Yeah, and that's right, that, it was a small proportion.
And I agree with the, you know, the judicial approach to outliers. We don't want to start, you know, throwing data out all over the place. Want to be very selective.
Great presentation, Katie. We really appreciate your efforts here. And we would like to have the other panel members. I think they have a few questions and comments. We'd like them to come up at this time. And and then following that, we'll have open discussion again from the audience. Yeah, so I'd like to ask all panel members, let's please keep your comment short to the point as we're running out of time. And let's start at this end with Tom Myers.
Just a quick question.
Microphone, please.
One quick question. You mentioned Frying Pan Lake has different parameters than the other lakes. I'm just curious, are they similar to the groundwater in the area or other surface water that may be flowing into or just below? I mean, how does it match up with other groundwater quality in the area of the lake?
Unfortunately, I'm not a good guy to answer that question because that's a very small detail of the surface water sampling program, and I wasn't responsible for the surface water sampling program, so I apologize. I'm not able to give you an answer on that.
Okay.
All right, Tom Al.
Okay, I just have one question, and it's not specifically related to water. It's and you maybe didn't have much to do with this, but there was sediment sampling done and reported under the trace elements chapter.
Yeah, that was completely out of my area. Yeah.
Okay, I don't know if there's anybody in the audience. I think it was SLR. Jane. Okay. Okay. Well, I think it's really valuable. Sediment sampling is an time-integrated sample of what the stream has seen, right? So I think it's extremely valuable. I guess I'm wondering about methods. There's analytical methods reported in the chapter or appendix, but there's no discussion, I think, of how the samples were handled. Is there specific grain sizes analyzed, for example? Can you...
As best as I can recall, they were basically a core of the sediment that went down so many inches, and there really wasn't an effort to do a lot of characterization in terms of grain size and things like that. It was just a core that was simply pounded into the sediment, and then probably the first 4 to 6 inches became the sample. It was pretty straightforward.
Can I take a second to put a slide up? Is that slide? I think in terms of baseline, sediments are really, really valuable. I've personally gotten myself out of trouble because of sediment data. But how you collect them and ensure that you're always comparing apples to apples is really important, right? And there's what I'm showing right here is just some data from there's this Arthur Horowitz from the USGS. So we always come back to the USGS, right? But there's a primer on sediment trace element chemistry, and I think it's probably worthwhile for your team members to have a look at that. What this shows is really, it says relative mass transport for different metals, but just think of it, because it's just discharges in there as a constant, just think of it as concentration versus grain size on the lower axis. And that's for any sediment that you might collect in a stream, for example. So if you collect a sample on one side of a stream and it has fairly coarse-grained material, you might get an analysis, say, I'm trying to get the microphone to work while turning. So if we look at manganese, for example, fairly coarse-grained material will give you low concentration in terms of mass manganese per mass sediment because the surface area is small. If you go across the stream, the sediment's been exposed to the same water over time, but maybe it's finer grained. You collect a sample here and there's a lot more fine-grained material in there, you will get a much higher concentration because of the higher surface area, right? So just as normalization of surface area allows you to diminish the precision or increase the precision that Katie was talking about, right? and allow you to sample and compare from time to time and place to place. And I think that's your data. If I think about it, the copper in the South Fork Cockatoolie was about twice as high as in the North Fork and the Upper Tulare. So I think that makes sense, and it's consistent with the water quality data. But I think just in terms of collecting good baseline data for sediment, which I think is very important, that reference is probably a really good
Yep,
one.
that's helpful, thank you.
Okay, Chris?
I just have one minor question. You showed a number of plots with a variety of water quality parameters ranked and plotted as a kind of a distance downstream, although it wasn't plotted as distance, it was just ranked. Well, I didn't understand why you did it that way.
Yeah, Mark's rationale was that he was doing a statistical test to distinguish whether there's a statistically significant change in concentration along the stream. And so then when he was presenting those plots, then he was presenting the plots in the context of the statistical test in order to show the order of the sampling stations, but he wasn't trying to represent the distance or anything like that, because that was not part of the test that he was doing on the comparison of water quality.
Okay, so it's a trend, but not really, because it's a value against something without a dimension.
Yeah,
So
what
it's-
it is the test is testing for differences between locations,
Okay.
but it doesn't care how far it is. Yeah.
Okay. That's all.
Yeah.
Okay, last chance for the panel. Any last comments, questions, suggestions? Okay. Thank you. All right, we'd like to open it up to the discussion and questions from the audience at this point. So please come forward to the microphone, introduce yourself, and